f takes the it takes an interval, which is a subset of R. This is kind of our time component, cross our vector space, which is Rn, and then maps this to. Sorry, I'm writing this very badly. It maps this to Rn. So again,
What exactly is X?
X is an open subset of Rn in this case.
Okay. Rn or Rn in the other dimension.
He uses the same notation, so I'm assuming Rn. It would have to be, n would have to be equal to n in this case. The equation we're talking about, the system we're talking about, is y is an element of this vector space. And the equation we have is that dy dt, through the linearity of vectors, we see this is the time derivative of each component. Y is a function of t is in this interval. Is equal to this, and we have an initial condition that y at some time 0 is equal to some initial value. So this is the system of equations that we're solving. What Taylor proves, and I'm not going to prove, but I will sketch a proof of, is that if this f is continuous where it's defined, and it satisfies a Lipschitz condition, which we write this way, these norms are again taken in Rn, they're taken in the same vector space. Euclidean norm, as far as I'm aware, although he doesn't discuss it.
Coefficient 1?
Yeah. And this is just a coefficient. It has no special properties other than it's constant. If this is true for all of the t in this interval that we're talking about, and for all y1 and y2 in this open set we're talking about, I think he means to say that this is just all of Rn, but he's saying open set, I think, just for generality. If this is true, then this problem here has a unique solution, existence and uniqueness of the solution to this equation. I can sketch a proof of that very briefly if you'd like, or we can stop. Do you guys want to see a brief sketch of this proof?
Could, I was thinking of if we can use the mean value theorem applying for one specific point and then go to the derivative to the end of that. The generalized mean value theorem for that.
So I don't know whether or not we can, but that's not what's done in this book.
Like there exists a point, if it's differentiable, there exists a point such that.
So what he uses is called Picard iteration, which you see over and over again in existence proof for first order ODEs, and probably in other places as well, is we construct a sequence of YKs where this is our initial condition. So we set this sequence and we guess an initial value. We can say, for example, that this initial function is just our initial condition. We guess some initial point in the phase space of this, or rather in just the y direction of
You
this.
should explain where this comes from. You take that differential equation and you rewrite it as an integral equation. It basically looks like this without k.
Right. So it's exactly that, right? We integrate this, and this will have a minus initial condition, right? A minus y0 term from integrating this. We can move that to the other side, that's here, and then this is just the integral from the initial time to t. Is that clear, or do you want to see that? Okay. So if we guess this, what he then discusses he discusses metric spaces. So I was going to ask, has anyone not had 471? Okay. Sam.
I never took it.
So has anyone not really dealt with metric spaces? Should I give a formal definition, or should we just sort of?
No, just three properties.
Okay. So, right, metric space is a set of points. We'll call it X. It's a set of points X, and we define a function on it called a metric, which maps it to R, really R plus, but that's one of the properties for all X and Y.
Well, not exactly X, Cartesian product of X with itself. D maps X cross X to R. It maps
Oh, of course, I'm sorry, you're right. Right, we call the metric space just X, but the distance function itself maps the Cartesian product, and then for all points in this set, and this can be an arbitrary set, we define this
You know
distance.
that there are the letters in Latin alphabet. You have too many X's and crosses.
Yeah, I should. We'll just. It maps a set B. It is symmetric. This is positive semi-definite.
Yeah. Transitivity.
And then, right, the triangle inequality. So if we have two elements of this metric space, we can always find a third element. It doesn't matter too much what it is. But for any other element, this will be true. And this is kind of a generalization of the triangle inequality in Euclidean space.
What
Well, you
is
forgot one that
Right.
of X is 0. Or you could say if and only if X is equal to Y.
Sure.
If X, Y is 0, if and only X
Right, so the distance of a point to itself is 0.
what is set B? Is that in Rn dimension or just
No,
have to be
an arbitrary set.
Arbitrary.
Metric spaces are defined very generally. We can get them, and maybe we'll go into this later, but we can get them from normed spaces. So any vector space where a norm is defined, we can take the norm of x minus y and set this equal to the metric of x and y. And this is called the induced metric from the norm, right?
And those are called Banach spaces.
As long as Cauchy sequences are complete, right? So, yeah, we'll discuss Banach spaces later, I believe. Where was I going? So anyway, what he discusses, and I'm not going to go into any more details here for a couple of reasons, but he discusses a contraction mapping and an operator on metric spaces, and he discusses that if we treat this as an operator on this metric space, that sort of shrinks the distance between yk and yk minus 1. If this operator applied to these vectors sort of shrinks this distance each time we apply it, then it's a contraction and it has a unique fixed point. And he proves the contraction mapping theorem and then applies it to this problem with this being the mapping, this yk being the mapping of the element. So I think that's all I'm going to discuss today. What did I do in time? And then Adil will, so what we're going, I guess what we need to talk about is what sort of book to work from, because there, I don't know, I sort of mentioned other people, we could look at other things, and it hasn't been set in stone that the Michael Taylor book is one we will look at. So there are several other choices. One that was suggested to me by two different people is Lawrence Evans. One problem with it is we do not have online access. Everyone here has online access through Springer to the Michael Taylor book. But I can kind of give you my interpretation of the difference of these two, and then I can be corrected as I'm wrong. This book, the Michael Taylor book, is far more geometrical and very sort of invariant, talking about differential forms and trying to put these operators in that language. Whereas this book is, as far as I can tell, only in Euclidean space. So in some sense, this might be more interesting to anyone interested in mathematical physics, and in some sense, this might be more interested to people who want to do more, I guess, applied things. That's not necessarily true, but that's sort of how I was told it by Dr. Kerr. So this book, from what I can tell, personally speaking, this does not mean it's the case, is easier to read, and kind of picks up where 438 left off, the second PE's course, whereas this book is quite a bit at a higher level, much more general, much more theoretical. So it's good in its generality, but it might be hard to really understand anything after we get out of chapter 1. But I don't know, what do you guys think?
At least so far, I mean, I'm not sure the books, I don't really have any input on those, but I don't know, it's presented very well, at least the way you're presenting it, but.
Why don't we study that? Because the general things like most of people know the notion and are really interested in the theory and things for the mathematical physics. But
Yeah, the book is openly accessible, I mean, that seems to be a bit of a plus.
Right. Anybody else? So one thing I can suggest is for next week, Adil, I think, wanted to volunteer to pick up where I'm leaving off.
Are you
Okay.
stopping now? Or you have another half an
Well, I
hour?
thought we would discuss this more. I have a little bit more, but I'm much less prepared to give it. I
Why
can.
don't you do that? I mean, it would be fun to see
Sure.
how do you sound when you're less prepared. Well, let me say a couple of words in these
Sure.
books. Well, I have both of them. Well, I like the Taylor's book way more than the Evans book, and so I like it very much. It's a fundamental kind of treatise. It has 3 volumes. It has everything in it, and it gives a very good preparation, like for the whole what follows. And well, the idea of this seminar, I guess, was to get some exposure into some experience and to get excited. And don't expect that you will know that stuff. I mean, for that you need to take course and to study that book thoroughly. So, and for that, this book is good. I mean, you don't need to understand all the theorems, and whoever will present next stuff, I mean, you just need to explain the ideas and what's in there, and you say, okay, here's the theorem, and I'm really not sure how to prove it, but I mean, they use this and that. That will give you much more useful than spending, months on some proofs that you'll never really see, and it even may kill your interest in that thing. I mean, because you'll be buried in the technical details. That book is, as I said, it's much more geometrical. It has Hamiltonian system. It has symplectic geometry. It has vector fields. It has completely integrable system. All already in the first chapter. So it's it's some people would ask about, like Adil was asking about those things. It's already here. This basic gives you kind of an idea what comes next. And then, well, you have everything. And those, if you want to go into depth, then there are some appendices, or you could consult some, I don't know, faculty, it could come to me, or, but I really think that most of the people would benefit from this seminar much more if you use that book.
Sure.
Well, there are thousands of books. It's a very old subject, and that book is much more modern. In particular, in the second volume, there are applications and some really exciting stuff that, I mean,